Welcome back to PV Online Chemistry. And today we're going to take a look at the electromagnetic spectrum, or the light, when we're taking a look at light. There's a couple of relationships that's going to be very important to us. One is going to be energy, the energy of light. Since all of our energy does essentially come from the sun, it's going to be important to understand the relationship between wavelength and frequency. All right, you can't see this very well, but there's a little yellow dot moving, and so that's going to be looking at a wavelength. Now, wavelength, we're going to use the symbol lambda to represent the distance. So it's a length, so it's going to be in terms of meters. When you're looking at light, it tends to be pretty small, so you're going to see some metric prefixes that you probably haven't seen up till now. Nanometer is 10 to the negative ninth. All right, so the unit of wavelength is small, so you can see nanometers, or you can see micrometer. Micro would be a millionth of a meter. Frequency. Frequency is basically how many cycles occur or how many waves occur in a given second. The unit that we use for frequency is called a hertz. You're probably familiar with that with your computer. The operation, it's how many operations occur every second, and that's going to be gigahertz, megahertz. So when you're looking at RAM, this is real important. It's telling you the frequency, how many processes occur every second. Now, this relationship here, the speed of light is constant. It's 300 million meters per second. And so that number is a constant, which means then that the wavelength and the frequency, wavelength is lambda, frequency is going to be, it looks like that V. And so those two are always going to multiply so that it equals 300 million meters per second. Now, this is going to have a consequence that's going to be important to us, and that is that as the wavelength gets larger, the frequency has to get smaller in order for those two values to always equal 300 million meters per second. So you can rearrange it. They are inversely proportional. So since the speed of light is a constant, the wavelength and frequency are inversely proportional. What that means is as one gets large, the other one has to get small. All right, so let's take a look at this. We want to find the frequency of blue light. It's got a wavelength of 450 nanometers. Since the speed of light stays constant, we'll use that, 300 million meters per second. We can rearrange our equation, and we can calculate the frequency. And you can see the frequency is 6.67 times 10 to the 14th. Seconds to the minus 1 is also a hertz. The frequency is going to be very large, particularly when you're looking at visible light. So don't be surprised when you see that. Okay, typically we think of light, we narrow our scope into visible, but in fact the electromagnetic spectrum is quite large. When in your science class, whether it be physics or chemistry, when they're talking about light, that will incorporate these other forms of light as well. X-rays, infrared, microwaves, radio waves. And so basically what happens is they're going to be determined by their frequency. Notice that if you have a high frequency, the wavelength is short because of the inverse relationship. Now we take a look at the electromagnetic spectrum. This actually should be smaller if we had it to scale. This is the visible. This is what we see, but you can see, look at how big the electromagnetic spectrum is if you include the other types of light. Okay, so let's take a look at this. Light with a wavelength of 0.5 micrometers, will it have a frequency more or less than light with a wavelength of 0.2 micrometers? All right, so remember there's an inverse relationship, meaning that if the wavelength is longer, then the frequency is going to have to be less. It's going to have to be shorter. Now let's take a look at this. So this is our electromagnetic spectrum, and right in this area is going to be your visible light. So now the visible light is going to be the section that you kind of want to have your frame of reference. Now radio waves are going to be pretty long. As a matter of fact, years ago we used to have antennas which were about the length of a radio wave. So radio waves are going to be very long, and so if they're long, then that means their frequency is going to be pretty small. Okay. Now let's take a look at the next one, X-rays. All right, so now X-rays are going to have, the higher the frequency, the higher the energy associated with it. That means the more damage to you. So keep in mind that frequency and energy are related. So in order to have X-rays are going to do harm. They can do harm to you. So they're going to have a much higher frequency. So let's put those over here. And we've got it's going to be shorter wavelength, higher frequency. Now we have infrared. Infrared is going to be something that doesn't do damage to you. It's going to butt up against the red portion of the visible spectrum. There we go. I put it too close to the visible light. The infrared is going to be adjacent to the red portion of the visible spectrum. Basically what this does is this is going to heat up, this is going to make the atoms wiggle. So it's not going to cause any long-term damage. Now we go to gamma rays. Gamma rays are bad. So that's going to be the highest frequency, which means it's going to have the really short wavelengths. Always think in terms of what's going to happen to you. And so in terms of light, X-rays, gamma rays are going to be the worst for you. Over here, infrared just makes the atoms wiggle. Radio waves are just really long, so they're not going to do anything. Now we get to microwaves. Microwaves are going to have a long enough and a short enough frequency. They're not going to do any damage. And then last but not least, we have our ultraviolet. And we know that being exposed to too much ultraviolet in the sun is going to do damage to our skin. That's how we can get skin cancer. It also is going to be adjacent to the violet portion of the visible spectrum. So always remember that the higher the frequency, the higher the energy, the more damage. The higher the frequency, the shorter the wavelength. And that's how come they can penetrate through your skin and go in and do cellular damage. On the other side, when you start looking at the shorter or the longer wavelengths, the longer wavelengths are going to have the smaller frequencies, less energy, less damage. And there you go. See you next time.